Yeah, hello everybody. Welcome to this very exciting asset colloquium. Professor Mahadevan is going to speak about exoplanets and habitable worlds, and it is going to be a very exciting thing. And I request Joe Ninan to please introduce the speaker, Mr. Adivasi.
Thank you, everyone. So it's a great pleasure to have Professor Suvrath Mahadevan here for giving the asset colloquium. So Professor Suvrath Mahadevan is known in the EPRV community for coming up with not just one or two innovative solutions, but a series of innovative solutions which kind of really push the frontiers of exoplanet detection technology. So Suvrath actually did his engineering physics BTech here in IIT Bombay back then, and then moved to Penn State and University of Florida for PhD and further. So now he's at Penn State, where he built numerous instruments. The most recent of them being the Habitable Zone Planet Finder and the NUID instrument, two extremely precise radial velocity spectrographs in the world. So he is currently Verne M. William Professor at Penn State. He's a recipient of numerous awards from Michelson Fellowships to most recently the NASA Group Achievement Award for the NUID instrument and the work related in the EPRV. So with that, I invite Suvrath to give us a colloquium. Thank you.
Thank you, Joe, for that very kind introduction. It's a real pleasure to be here at TIFR. I actually got my first experience building astronomical instruments here in TIFR as a VSRP student working in Professor Manchanda's lab a few years ago, about 1999. So it's a real pleasure to be here to talk about some of the stuff we're doing. And often we talk about the science that comes out of the instruments and kind of relegate the instruments themselves to a footnote. So here I was hoping to rather open the hood of these instruments and tell you all the things it actually takes to do precision radial velocity and exoplanet discovery at the level that we want to, which is really at the level where we can discover Earth analogs, planets like our own around sun-like stars. And that turns out is actually quite a difficult problem. But again, we live in a golden age of exoplanet exploration. In our lifetimes, we've gone from knowing 0 planets around stars outside the solar system to knowing something like 5,000 or so. And a big part of that is technology. Our measurement metrology and techniques finally caught up to our aspirations after thousands of years of, as a species, philosophizing about life outside the solar system. We are actually now in the process of actually making rigorous claims about where these planets are, how we might even go about the search for biosignatures, and where those planets might be. So there are planets on other stars, and we're interested very much not just in the bulk properties of these planets. The formation is very interesting too, but we're interested in where now near the sun can we actually find the planets that we can go look for biosignatures around. So a big part of my talk will focus on the instrumentation that will hopefully get us there, but also talk a little bit about the other things that we are finding with this instrumentation that are kind of pretty interesting as well. So before I launch into this, I want to say that Earth-mass planets are actually possible to detect. In fact, the very first planets outside the solar system, the exoplanets around this pulsar, PSR B1257 plus 12, that Alex Walshin and Dale Frail discovered more than 30 years ago at this point in 1992. One of those planets is Mars moonish mass. It's much smaller than the mass of the Earth. So it is possible to find Earth-mass planets around sun-like stars. So of course, some of our colleagues in the audience will immediately spot the issue here, which is that, yeah, if you have an exquisite clock on your star, a lot of things are possible, including possible detections of the gravitational wave background with pulsars. So pulsars are exquisite. But the punchline also here is if we can measure frequency, we should always measure frequency because we can measure frequency better than we can measure almost anything else. In other words, we can measure time better than we can measure almost anything else. Recall the SI definition of the second, a certain number of transitions of cesium that we count and then say that's a second. In our lifetime, this will change. This will either become some sort of nuclear transition or a rubidium fountain or something like this, right? So this is always changing. We're always becoming more precise, but this is how we define the second. This is the speed of light. What happens if we measure the speed of light better? Does this number change? So this is a constant in the SI system now. The second is very, very well defined. So if we measure the speed of light better, the definition of the meter changes. It's no longer that rod at PTB, it's actually this constant coupled with the second. So again, we can measure time exquisitely well. So, okay, you say, okay, we don't have, normal stars don't have clocks. But there's an analogy to this timing. It's a coarse analogy because it's not as precise, but it still gets you pretty far. This is TRAPPIST-1. This is a late M dwarf. Its mass is something like 10 or 11 times smaller than the mass of the sun. It's the size of Jupiter. It's about as low mass as you can get and still be called a star. This thing has 7 transiting planets around it. We can time the transits of those planets. And it turns out that this is in a Laplace resonance, a very, very unique resonance where all the planets are actually in integer periods of themselves, of their orbital periods, which means that they interact dynamically. We can time these transits and the change of the timing of these transits and infer dynamically the masses of these planets. So you can see in a planet radius versus planet mass plot, the TRAPPIST-1 planets actually lie in a line that is not that different from the terrestrial planets. So when I say it's going to be hard to measure or find Earth mass planets, that statement is a bulk statement. There are extraordinary objects like pulsars where we unfortunately don't think we can find life. The environment is just too extreme. There are extraordinary objects like TRAPPIST-1, which are gifts from the universe. Actually, TRAPPIST-1 is one of 2 or 3 systems where the James Webb Space Telescope even has a shot of measuring an atmosphere. And the bad news is so far, doesn't seem like any of these planets have an atmosphere, although there will be more telescope time dedicated because, it's one of those analogies where there's a lamppost, you might as well look where there's light because you can't look anywhere else. So if we can find an atmosphere on these, it would be great, but the chances don't look that great right now. So also back to the clocks, right? The modern clocks, and my apologies to my pulsar astronomer colleagues, but the modern clocks are better than pulsars. Right? There was a debate about this about 10 years ago, but the NIST folks and the lab folks have just moved on. At this point, the best clocks, you can measure the difference in the beat rate of the clock from the bottom to the top because of a gravitational redshift. Over a couple millimeters, the clocks diverge because they see the gravitational field of the Earth. Right? The clocks are just exquisite. So if we can measure time, measure frequency, we should measure frequency. So after standing on this bully pulpit and going about how awesome frequency is, I'm going to tell you about how that's not possible because sun-like stars don't have a clock on them. We have to come up with a slightly different way of doing this. And this was what Michel Mayor and Didier Queloz did in 1994. This was the first planet around a sun-like star, 51 Pegasi b. It was a hot Jupiter, a Jupiter at 4.5 days. Nobody expected this. Completely unexpected discovery and very well worthy of the Nobel Prize. Yeah, 4.5 day orbital period. Mercury is 88 days, by the way. So it's really, really very close in. It's a hot Jupiter. Yeah.
So what's the signal that they accidentally discover what was?
Yeah. So they had built this instrument, LOD, which is a successor of instruments that had built to actually kind of look for signals like this. They weren't necessarily looking for 4.5 day signals, but when they took the data, they folded it and the signal appeared. They decided to be cautious and wait another season to see if the signal was persistent, and it was. At that point, they were sort of convinced that it was a legitimate signal. It took the community a little bit longer because there were certainly some people who thought it was a stellar activity signal, but it ends up that it really is a planet. So what is the signal? Great question. So it's the Doppler radial velocity signature of the star. So we're taught that the planets orbit the star, but the reality, of course, is simple Newtonian mechanics. The star and planet are orbiting a common center of mass, right? So the planet is tugging on the star. That tug is just very, very gentle. In the case of the Earth, if you were on the plane of the screen, the spectral lines would move in velocity by about 8.9 centimeters per second over a year. The hot Jupiter that I showed you, that was more like 50 meters per second over 3 or 4 days. right? So hugely different signatures. And you can see why the hot Jupiters were the first things we discovered, because they are the largest signatures in the shortest orbit. So it's natural that if those objects existed and were not rare, we would find them. And it turns out that they're not that rare, like 1% of stars or so have. So we disperse starlight with large instruments, with large spectrometers, and we look for subtle shifts in the position of those spectral lines. The spectral lines, of course, come from the stellar photosphere of the star. They're made up of things like, iron, nickel, cobalt. Iron actually has a lot of lines. Vanadium, name your favorite element, it's probably in here. Even helium lines exist. Hydrogen has big absorption lines. So many lines make up the stellar photosphere, and they're all markers that we use for our Doppler shift. So there are two main techniques to actually make these measurements. One of them is called the simultaneous reference technique, where what you do is you build an instrument, you build a spectrometer, and you have two optical fibers. One optical fiber goes to your telescope, it looks at the star, and the other optical fiber goes to some calibration source that helps you figure out how your instrument is drifting. So it's a simultaneous calibration, and it works best when your instruments are actually stable, because you don't want your two fibers drifting relative to each other too much, otherwise the thing doesn't work. The other technique is something called a self-reference technique, where you put in a cell, an iodine cell, in your beam path, and you've measured the spectrum of the iodine in gaseous form, because iodine sublimates, at very high spectral resolution. And then you take data and you say, I don't really care how much my instrument drifts. Let it drift, because I know what the lines of iodine are intrinsically, and I'm just going to deconvolve out everything and measure the drift. And that also works reasonably well. But the nice thing about it is it is suitable for any split spectrometer. It doesn't have to be an ultra-stable spectrometer. But it's a restricted range, 500 to 620 nanometers, because that's where iodine has lines. This doesn't work in other regions where iodine doesn't have lines. It does require deconvolution, and as we know, deconvolution is a bit of a noisy process. So you need higher signal to noise to get the same level of precision, usually, as you do with this technique. Yeah, so that's been tried. Hydrogen fluoride has been used. Hydrogen cyanide in very sort of low concentrations has been used. And yeah, that's possible, but it turns out nothing quite has the nice density of lines that iodine has. So turns out that it's actually a little hard to find something like iodine in other band passes. Yeah, that's also been proposed. Actually, I wrote a paper in 2009 about using a series of cells, but it quickly gets pretty clunky, actually. So yeah.
It is also a popular source for locking lasers.
Yes, exactly. Yeah. Yes, absolutely. The lines are very well known. It's a well-behaved thing. Once you control the temperatures, it's pretty good. There are some other techniques. There's this thing called externally dispersed interferometry, where you can actually tap into the information without the high resolution by playing tricks with spatial heterodyning. There's also direct heterodyne spectroscopy, which in principle you could access these frequencies directly. And actually, this will be one of my last slides, where I'll show that this is possible, although with poor noise properties, but still very possible. So we've done this on the sun, but it's unlikely that we'll be able to do it on other stars. So for a history of the technique, so in about the 60s, we were able to do about kilometers per second radial velocity precision. And when I say radial velocity precision, I'm talking about differential radial velocity precision. How precise is your measurement when you measure the star and you measure it again? Not so much do you really know the center of mass motion of the star, because that turns out is a much harder problem. So this is a differential measurement. As the planet tugs on your star, can you measure that differential motion very well, as opposed to an absolute motion of the star? By the mid-80s or so, we were at 300 meters per second. Then we had the sort of in the 90s, we had things like LOD, which were 5-10 meters per second. And you can see this is when we found the planets.
Was there a Canadian?
Yeah, there was Gordon Walker's. There was Gordon Walker's. It was a little worse than this, but very comparable. Gordon Walker was actually looking for Jupiter analogs. So he was really looking for things at 12-year periods, but it ended up that the easier plans to find were the 5-day, 4-day things. 2000s, we ended up with HARPS, which was an ESO instrument that kind of really showed us how to get down to a meter per second or lower. And today we have a sort of generation of instruments, one of which that I'm a PI on, and Dr. Neenan has also worked on a lot. But there are a few others which are really pushing down below a meter per second, consistently well below a meter per second. But we're also running into this problem here, which is that the stars are no longer these nice clean light sources. You can barely make out the signal from the stellar activity because stellar activity becomes a dominant.
This was checked out with the sun.
No, you cannot detect the Earth because you're on the Earth. So we have done it on the sun. I'll show some slides on and plots on the sun, but you have to take out the motion of the platform you're on. And then you go, okay, well, I look at Jupiter, but turns out Jupiter that you would easily detect in another system is very hard to detect from here because you have this weird synotic chopping between the orbit of the Earth and Jupiter, and you can't really easily detect it either. Yeah, we always do this at the Solar System Battery Center. For what we need, the JPL Horizons is good enough now. The pulsar folks are good allies in making things always better, but I think it's usually pretty good. I mean, we do need to know where Ceres is reasonably well, but you know, everything else I think at this point is fairly well. Yeah. Our gratings are pretty big. When I say we're dispersing, we're talking about like macroscopic dispersing elements here, things that are ruled very precisely, coded very precisely, built on some of the more stable substances. We have Zerodor in this case, or ULE, things that thermally expand very little, but turns out everything moves a little bit. So we do have to calibrate out these drifts. What does 10 centimeters per second look like on your detector? So this is a scanning electron microscope image of a silicon detector. And this is representative of NUID or Express or something, roughly the dispersion everybody uses. This is the individual silicon atoms. So we are trying to probe 3 or 4 lattice spacings of the individual silicon atoms from light that has come from many light years away. So it's a bit of a crazy measurement to try and do, but this is what we're trying to do, right? We're well under, like, this is already 1,000th of a pixel, and we're trying to do like 10,000 or 100,000th of a pixel measurements. Very hard measurements to do. So we do it not on one line, we do it on a whole ensemble of lines from all the way to the visible to almost the near infrared in the case of HPF, or actually in NUID or HPF would be infrared. In NUID's case, the detector is actually 9K by 9K. The detector is literally as big as my head. It's this big. It's a monolithic detector. We would measure the cross correlation function of all the lines together and construct a radial velocity by fitting the peak. Right? And you can see that this nice line is already not a Gaussian because it encodes stellar astrophysics. Granulation is encoded in that line and actually turns out makes the line non-Gaussian already. And then you're trying to measure this very, very tiny shift on the detector. But you also want to find planets. You want to find not just any planet, but specifically for biosignatures in life, which is what I'm focusing on in this talk because it's a hard measurement to make. You want to find planets in something called a habitable zone, a range around the star where liquid water could exist on the star surface. It's also called the Goldilocks zone because too close, it's too hot, too far, you're too cold. There's a just right zone around the star. For a sun-like system, it's about 10 centimeters per second. But if you go to cooler, dimmer stars, M dwarfs, turns out that number actually increases to a meter per second because the stars are less massive and they are cooler. So the habitable zone moves inwards. These are also the more numerous stars in the stellar neighborhood. So we actually built an instrument called the Habitable Zone Planet Finder, not the Habitable Planet Finder, because you have to actually look at the spectra of this planet to figure out that it's really habitable. On the 10-meter Hobby-Eberly telescope, which is way out in the middle of nowhere in West Texas, it's actually the darkest site in the continental US. You have to go to Hawaii or Chile if you want to be at a darker site on either of those continents. It's called McDonald Observatory, and the HPF is a 10-meter telescope that's at that observatory. We also built NUID, which is another instrument, but optimized for sun-like stars, works in the visible, whereas HPF works in the infrared to tap into the light of the M dwarfs, because the M dwarfs emit in the infrared. So the other thing you can do with radial velocity is not just discover planets, but say you had a planet that was transiting, and here's a good example of a planet transiting the sun. The Earth transiting the sun is something like an 80 part per million dip for 8 hours. Whereas if you have an An Earth-like planet transiting a M dwarf, that dip is much, much more than 10 times larger, right? Because the star is smaller, so you're obscuring the star better. You have a transit, you can put radial velocity and transits together, and you can get planet mass, planet radius, and put it together and create planet density. So back to that plot that I showed you about how we can actually infer now compositions of planets. And we always get excited by this, but we don't get too excited because all we have really is density. And we don't overinterpret it, but you can make reasonable compositional inferences or assumptions. For example, you can say these planets clearly not 100% iron, even compressed, clearly not 100% water. Even things like magnesium silicates with some water don't work. What really works is sort of solar system type compositions or complete magnesium silicate under compression compositions. So you can actually begin to do planetary geology a little bit with these techniques. So, also, by the way, if you actually want to get James Webb Space Telescope data to characterize any planets, it's almost a requirement now for transiting planets to have mass. Because if you get a spectrum and you don't have mass, you're not really interpreting that spectrum properly. So you really need mass. The other thing you need radial velocity for is the next generation of missions, Habitable Worlds Observatory, or what used to be called LURE, or what is called LIFE, where you want these missions that will actually go take a picture with the coronagraph, dim out the central star, take a picture of these planets, and get spectra of the atmospheres of these planets. Without these spectra, we cannot make any inferences about biosignatures or habitability or their atmospheres. So we really need these spectra to understand these planets. The only way to do this is for Earth-like planets around Sun-like stars is from space with 6, 8, 10 meter apertures. But if you fly a mission blind, you're going to spend a lot of time just searching. Right? And these are very expensive missions to fly. So it's better to actually know where these planets are, at least where a subset of these planets are. And these planets actually are some of the most important high-value planets that we can go after. And only radial velocity currently will be able to really do this in a meaningful statistical way, because otherwise you're just waiting to get lucky with a transit. And that probability is not in our odds, right? It's a low probability event. No, you can do it inside one satellite. So there are two techniques to do that. One is you just have the normal coronagraph, which actually you have a LEO coronagraph, something just inside your coronagraph. The other is the star shade approach, right, where you have to have two satellites. So what happens there is if you just fly a circular aperture, you get a brightening exactly where you want a null because of diffraction. You get Poisson spot or Arago spot. So these star shades are designed very carefully to cancel out the higher order Fraunhofer and Fresnel refractions. Beautiful, beautiful designs, but they're not currently baseline to fly. It's the internal coronagraphs that are currently baseline to fly, but we're 20 years away. Who knows what's going to happen? So what do we need to actually detect these planets? You obviously want the instruments, and we'll talk about the instruments. You have to understand something about the stars. And you need significant amounts of observing time. This is not a game that you can play with a few nights every month. It's very hard. You actually need significant amount of time on your telescopes, on your instruments, which sometimes is in your control and sometimes is in the control of the time allocation committee. So you really do need a lot of time to do this. So I'll talk a little bit about HPF and NUID, which seem a little similar from outside because, of course, the heritage and the architecture is similar, but they're designed for different things. The one goes on this 10-meter telescope in West Texas. The other goes on the WIN telescope, which is an excellent 3.5-meter telescope at Kitt Peak, Arizona. One is optimized for M dwarfs. The other really is optimized for sun-like stars, although does very well for early M dwarfs as well. One's internal temperature is about 180 Kelvin, but uses an infrared detector, so it has to be kept cool. The detector, of course, is cooler at 120 Kelvin. This one's actually kept at 300 Kelvin, so slightly elevated from room temperature, so we can control it. It has a CCD instead of an infrared detector, and the detector, of course, is also kept cool. But when we talk about these instruments, they're just not spectrometers anymore. There are just too many things going into this to even call these spectrometers. They're really sort of precision radial velocity systems, right? So you need to control the temperature extremely well. You have to worry about the actual design of the instrument to make sure that the aberrations are minimized and the aberrations don't change with temperature. You have to worry about the telescope port. How are you coupling light into your fiber? Are you doing that in a very rigid way so that you don't move the light around too much? You have to worry about the pipeline because the reality is anything that you can't fix in hardware always becomes the pipeline's problem, right? We try not to make this true, but always something comes up and then the pipeline has to deal with it. So the pipeline is absolutely important. Turns out that you need to know the midpoint of your exposure to about a second or better for the barycentric correction to be good enough that it's a non-issue at the 10 centimeters per second level. And turns out that midpoint of the exposure is actually chromatic because clouds might come through, the blue light might actually fade a little bit more than the red light. So you actually have to have an exposure meter that's a little bit chromatic that has some multi-band pass or a small low resolution spectrometer of its own right, so that it tags the arrival time of most of, well, not individual photons, but that you can calculate the centroid of the exposure to better than a second as a function of wavelength. You actually have to worry about the fiber feed, worry about the detector, the charge transfer efficiency of the detector and the efficient detector really matter. In fact, for the Newitt detector, reading out the detector actually was causing more thermal noise than 10 centimeters per second could allow. Of course, you have to read out your detector. So we actually continuously shuffle the charge in the Newitt detector to dissipate out the heat. So we have to play all kinds of tricks to actually make the whole thing continuously stable. Worry about your calibration sources as well, which I'll talk about a little bit. Okay, so this is Newitt's optical design. Light comes in here. It's a large parabola. It's this gigantic grating that I showed you, goes back to the parabola. It's the fold mirror. This is just for like practicalities of fitting everything in. Hits this parabola again, goes through this large prism that disperses light in this cross dispersion direction, whereas the grating is really doing the bulk of the high resolution dispersion in this direction. And then there's just a camera that reimages it onto the CCD. This whole thing is pretty huge, but particularly huge is this prism. This prism is gigantic. So this was almost the entire Earth's supply of this particular glass for half a year or a year when we bought it, right? And this glass is used for lithography a lot, so we did buy a huge chunk of it. Visible. So Newitt actually goes all the way from 350, which is roughly where the atmosphere cuts off, to about a micron, which is roughly where silicon cuts off. So pretty much everything we can do with the visible we cover. And there's a reason for that, I'll talk about that. HPF, on the other hand, is very similar, except instead of a prism, we use a cross dispersion grating here. Instead of one mirror, we use two mirrors because there was some advantage to doing that. And instead of a CCD, we have an infrared detector, far more expensive, far pickier, far more annoying to work with. But if you want infrared data, you got to sort of, deal with the detectors. So here, there was a brief patch of time where we had two instruments in our lab, HPF in the front and Newitt in the back, and it was a completely crazy time in our lab. But you can see that here is the design of HPF, and you may think that there's a lot of empty space here, but there's beams crossing all over the patch. We had trouble putting even a simple baffle in because the light's just crossing all over with the design. But this is essentially what the instruments look like. They're heavily instrumented with temperature sensors and very well controlled with temperature as well when they're closed up. So what we have is the science fiber that goes to the telescope. But then we have a sky fiber that's just looking at a blank patch of sky near the source. So you can look at the emission lines coming from the sky because the sky has OH lines and other lines that you want to subtract out. But you also have this calibration fiber, and you can see there's a beautiful calibration source here, which almost looks too good to be true. It's the frequency stabilized laser comb. It's a picket fence of laser lines. The frequency of each line is known to better than 1 millimeter per second. And that comb is tied back to the reference hydrogen maser at the basement of NIST or something through the GPS system. So this really encodes into it our frequency definition of a second. We've taken that out of the basement of some government lab that's in charge of time and transported that information to your telescope, which is a pretty amazing thing you can do with laser combs. So the inner architecture of these devices, we have control heaters that actually keep the radiation shield at a specific temperature. We don't actually control the inner temperature directly. We control this box and then let the whole thing equilibrate It's almost like the whole thing is buried in a black body. There's a liquid nitrogen tank here. There's a getter cryoplate here that also contains charcoal getters to keep the vacuum very pristine. And then we have a very nice vacuum system here with the optics going in there. The fibers come through these penetrations. Various cables come through these penetrations. But we obviously have to pull a vacuum here for, this is, let me see, this is HPF. Yeah. But the innards of NUID would be different, but this architecture would be the same. So the reason we pull the vacuum is multifold, but one obvious reason is the refractive index of air is obviously not 1. In fact, if you calculate the difference between air and vacuum, that is equivalent to about 80 kilometers or so, right? So if you just pull vacuum, you're going to change your wavelength by 88 kilometers. So if you weren't in vacuum and a small pressure front comes through, changes atmospheric pressure by 10%, you could be off by 8 kilometers. And we're talking about 10 centimeters here, right? So just pull the vacuum. We just pull the vacuum to the point where the refractive index of whatever is left in there is effectively 1, and this becomes a non-issue and not a source. But there's another reason we pull a vacuum, which is that we want to isolate the instrument completely from the outside world. And we do this in the following way. So you have your optics, you have your vacuum boundary, or what will become your vacuum boundary. And right now the optics are talking to everything quite nicely. You have conduction, convection, radiation. You break conduction by actually being very careful how you design the bench. It's actually hung on G10 struts, very low conductivity struts. But you break convection by pulling the vacuum to a very high level. So then the molecular transport is stopped. But the molecules are largely gone. I mean, there are always some molecules, but the shorting that you get with the convection is gone. So you are left with radiation, though. The optics are talking to the vacuum, outside vacuum shell. So what we do for that is we put what is known as multi-layer insulation or space blankets. We actually built our own space blankets in-house for both NUID and HPF. You do that, you've broken conduction, convection, radiation, or almost broken. It's impossible to isolate anything completely from the outside world, but you've almost broken it, and you get sort of temperature stabilities at the sort of sub-millikelvin level, which means that the whole instrument is stable to sub-millikelvin levels, which is pretty extraordinary. So this is what it looks like when it's almost like a birthday present wrapped up, but it's the instrument wrapped in its multi-layer insulation, and these are the temperature stabilities we get. So over many, many, many days, we're sub-millikelvin. Even over months, there's some very slow drift, but look at the scale. The RMS is only about 2 Kelvin, which is very slow, and you can calibrate this out. Within the day, which is where you do the calibrations, you do a morning calibration, evening calibration. Within the day, the drift is like, fraction of a millikelvin, extremely, extremely stable. So we've really taken a lot of work, a lot of effort to make these instruments extraordinarily stable instruments. The other thing you have to worry about, once you've built a very stable instrument, is it's no good if the light coming into the instrument is dancing around. We have optical fibers, and you go, but optical fibers are great. They should completely remove all memory. Turns out they're not that great, right? And these are multi-mode optical fibers, not single-mode optical fibers. As you change the input on a circular fiber, you will actually get a huge change here in the output. So all your efforts to stabilize your instruments are completely useless because the light is moving around in the input of the focal plate. So what we have to do is we have to use these octagonal fibers, and this is actually a movie, so the fiber is moving around, and you can see there's barely any motion here. And that essentially means that the scrambling is pretty good, but it's still not good enough for our needs. So we actually invented this little ball lens scrambler, where if you have a refractive index 2 lens, you can actually put 2 fibers on one side and the other and couple the near and far field of those fibers. So the fibers interchange near and far fields, and then this one scrambles the near field, then this one scrambles the near field. So you almost get perfect scrambling. And we had to do all this actually to bring down the error of the guiding to sub 10 centimeters per second. So it's not a big part of the error budget. The other thing we have to worry about with a fiber is basically just an electromagnetic waveguide. Yeah, we generally don't think about it in that way because it has many modes and light comes through, but the speckling tells you that it's really an electromagnetic waveguide. And all electromagnetic waveguides have a finite number of TE and TM modes propagating in them. over time, as the fiber stretches and the telescope moves, those modes are dancing around, which means that the centroid of those modes is also dancing around. So even if you have this perfect spatial scrambling, the fact that this is a waveguide means that there's a temporal change in the fiber that essentially moves these around. And our calculation was we could actually move around by 50 centimeters and things if we weren't careful about this. So we actually scrambled these fibers. We actually moved them at high frequencies during observations with a machine we built and with something called a giga scrambler to completely wipe out this pattern and drop it below 10 centimeters per second as well, so that this is not a factor in our calculations. Yes. Yes. Right. So for the calibration source, we actually have a device that very quickly disturbs it at very high rates, tens of hertz. For the starlight fiber, and this fiber is the one that you do not want it to break, right, because it's going straight to the telescope, we're a little more gentle with it. So we've built ourselves a scrambling device that sort of does this 1 hertz motion. So it sort of it mimics a human arm doing this, because it turns out that actually works pretty well. So it just switches on whenever data is taken. It moves the fiber gently at sort of 1 hertz or so, and that works extremely. So I talked about how everything drifts. We really want these frequency combs, and we have these frequency combs with HPF, and you can see here picket fence of comb lines just dancing across the whole detector, thousands upon thousands of laser lines that you can just lock onto. The frequency of every single one, exquisitely stable, really tells you everything about your instrument drift. The one we use for HPF is something called an EOM comb, or an electro-optically modulated comb. We actually built this one in collaboration with a group led by Scott Diddams at NIST and the University of Colorado. And essentially you have an EOM comb generator, which you use this light and go through the silicon waveguide, go through something called a spatial light modulator. So you even out the flux of the comb, otherwise it comes out too bright and too faint. And then eventually that goes into the telescope and into our spectrometer and looks like this. The HPF comb is currently the longest running, most reliable astro comb in any sort of telescope or any sort of survey. A lot of development is happening in combs, but the one we built just happened to use telecom components. We were in the infrared, really helped us be very, very stable. We also have for NUID a Menlo comb. This is a company that we purchased a comb from. And this also is in the basement of the WIN telescope, and we use the Menlo comb in the optical for NUID. It doesn't go super blue. It tends to peter out about 500 nanometers. We would like it to actually go to 350 or at least 400 nanometers, but we haven't been able to accomplish that yet. This is what the HPF comb looks like. Lots of nonlinear optics. There is, of course, a kill switch for a laser here because there's a 40-watt laser bouncing around the system. There's a silicon nitride waveguide where a lot of the amplification happens, and you can see that under sort of a zoom here. The piezo stage that actually carefully aligns it so that the laser is always going through the system. Takes a little bit of work to keep it going, but it's extremely stable. It's extremely high uptime, and we're very happy with this comp. It's been running for almost 3 years, 4 years now, and continuously in use as a calibrator for HPF. And we can get down to like 20 centimeters in a comb minus comb way. So we are actually pretty good. Remember, for HPF, we don't need to get down to 10 centimeters. We only need less than a meter per second, and we're well in that territory for planets around M dwarfs.
All the big three?
No, similar, but not same. Because if you really wanted to make it same, this spader itself would need to be in a shell spectrometer. So you can address each individual peak, right? Right now, it's just a one-dimensional spectrometer that you coarsely sample the light and say, oh, this is too big, this is too small. So on order by order level, you can change things, but you will get factor of a few variations. The other thing we realized is, because we were paranoid about these combs not working, they were emerging technology. So we had etalons as well as sources. Etalons are artificial calibrators. The peaks are stable-ish, but they're not pinned to any atomic standards or any frequency reference. But one thing we were seeing was our etalon, which lives in a vacuum and has ULE and mirror coating, so should be very, very stable. we were seeing wavelength or frequency dependent drifts, which you should not see. It should just be the velocity drift of the echelon should be constant across all frequencies or wavelengths, because the only thing that can change is this spacing here, right? And we were quite puzzled by this. And the only reason we were even able to see this, because look at the measurement numbers here. We're talking of mode shifts of a few centimeters per second over quite a long period of time. The only reason we could even measure this is because we had the comb, which was giving us this exquisite measurement. Turns out that the outer layer of the echelon coating is moving a little bit, and we were able to actually figure out that there's a small change or increase in the width as the coating stress is relaxed. These changes are of the order of picometers over time, but we were able to actually measure this very, very well. So even very small physical changes, these instruments are very capable of measuring, because they're trying to measure these exquisite changes on other stars. So this is our measurement of Barnard star, which is the next closest member of next closest star to the sun after the Proxima and Alpha Centauri system. And we can see that this is about 1.5 meters per second sigma. Extremely good radio velocity precision for the infrared, definitely enough to detect these planets. And NUIT does even better in the optical, because the CCDs actually turns out are better devices than infrared detectors, which have a lot of quirks still. And we can get down to about, in some places 30, 40 centimeters. We think our instrument actually is much better than this. This is all actually driven by stellar activity. So when I say that the instruments are probing sub-meter per second, internally to the instruments, it's often sub 10 centimeters per second. Day to day, they can be maybe 20 centimeters per second or so, but the stars are actually worse than that. So we found this very interesting object with NUIT, and I want to talk a little bit about, with HPF. I want to talk a little bit about other things we can do other than finding planets, or just finding Earth-like planets with these exquisite instruments. We found this planet. Actually, we first found it in transit. The transit is very weird. You can see, right? It has a chunk taken out of it. And you go, what happened here? And it's not an instrumental artifact. It's not something weird. It's astrophysical. What's happening is that the planet is actually transiting across a star spot in this pageant. And when it transits across the star spot, because the star spot is actually darker than the stellar photosphere, you actually get an enhancement of the transit depth. Of course, this enhancement will never go over the baseline because the star spot still is getting blocked. But we've been monitoring this over time, and we can infer from this what kind of distribution of star spots there is. And we're hoping to actually figure out if there is interesting exospheric properties of this planet that we can infer. So there are unique objects that we find, and we can confirm dynamically with radio velocities with these sort of instruments. It's evolving. We definitely see it evolving. But it was remarkably constant for a good couple seasons, but then it started evolving. We looked into that, and the numbers don't pan out. Also, this thing is chromatic, and yeah, so. But we still looked into that, and the numbers don't pan out. Okay, so the other thing I want to talk about is the other thing you can do with these spectrometers is actually probe the exospheres or the heliospheres of these planets. So this is done typically in two ways. You have a planet, and you have an exosphere on that planet. That exosphere you can detect in Lyman alpha, in hydrogen Lyman alpha, in the UV. So of course you have to go to space. It's a little annoying because you have geocoronal emission and things like that. But you can see this extended cloud of hydrogen that you can detect if you were able to observe this with, say, HST or some instrument like that. Alternatively, you can actually do this from the ground, where you can detect an exosphere of helium in 830. And there's been a lot of development in the past 5 years on this. It was actually originally proposed by some colleagues about a decade ago, but it's only really in the past 5 years that these observations have made it possible. This you can do from the ground. This you can do with infrared spectrometers. One of the things we found with HPF, as we published in this paper by Zhang et al., we saw that we do see some absorption during the transit around HAT P32A, which is a fairly low density Jupiter at a late F star. But interestingly, what puzzled us was pre and post transit, we saw absorption as well, whereas farther away from the transit, we don't see anything. So we followed this up with the HPF because it's a Q-scheduled telescope. We can just go take data whenever we want. And indeed, we see that this totally pans out. It really is, there is an absorption outside the transit. Our speculation in our paper, actually backed up by fairly rigorous modeling, is this is a huge tidal tail of helium flowing out of the planet. Because this is a low density planet, it overflows its Roche lobe, and its interaction with the stellar wind then sort of pushes the helium backward and forward. So we're really seeing how stars sculpt planets and how planetary systems are getting sculpted almost in real time with these sort of probes, with these exquisite instruments. You could not do this with if your instrument was not super stable or if you could not trust your spectra. The other thing I said I would talk about is stellar activity and how stellar activity is really stopping us from finding these planets. And the problem with stellar activity is everything you care about in radial velocities has some manifestation due to the internal morphology or magnetic activity of the star. Oscillations, which range in timescale from seconds to minutes, convection or granulation, which also has timescales of minutes, flares that can be many minutes to hours, supergranulation, which is coherent motion of the granules, can be over days, spots, weeks, or at the rotation period of the star itself. And of course, on many year timescales, you have the 11 or 22-year cycle of the solar magnetic change. 22 years with the polarization, and 11 years if you don't consider the magnetic flip. So these are all problems. These all impact our lives in different ways. So rather than calculating one radial velocity, we really are beginning as a community to think about how tools like machine learning or how tools like thinking about the depth of formation of these lines and putting these all together. How can we dig out more information and actually tease out this activity signature? And this is the reason we cover all of the bandpass in the visible with NUID, because there are many different chromospheric and photospheric activity indicators, and we did not know which ones would be the best for what situation. So we did the classic astronomer thing of do them all, right? So NUID just covers all of the optical bandpass because then we don't have to actually make choices. We actually have all these indicators to let the data itself tell us which of these indicators, or maybe just which of these lines is going to be the most useful. So NUID covers essentially all of the optical spectrum. Of course, there's a lot of telluric water lines here, but we can work in orders also where telluric water lines are not. And turns out we can actually do fairly good telluric removal, although that doesn't happen in an automated way. But the other thing we did was the wind telescope takes data during the night. So we said, hey, let's not waste NUID time during the day. We spent a lot of time building this exquisite instrument. So one of my students built a solar telescope, this little Wally type thing that sits on the top of the wind telescope, wakes up every morning, looks at the sun, and NUID looks at that light from the sun, and we observe the sun pretty much all day for like 8 hours or so. This thing, of course, is at the peak of the mountain at one of the tallest points on top of the shed. So it's been hit by lightning a few times. It has survived, but then we also put a lightning rod near it so that it doesn't get hit anymore. But it got hit a few times and it survived. Of course, we know folding the data over many months, we can actually see the solar P mode oscillations very clearly in the NUID data. If you just fold the data, all the known P modes show up quite well. So we are probing stellar helioseismology and stellar astrophysics pretty well. So here is a plot where there's a comparison across 4 different instruments, all sort of state-of-the-art RV instruments, NUID, Express, HARPS, and HARPS not. This work was led by Lily Zhao. And you can see in this plot where everything's put together that when all of these instruments are sort of observing the sun at the same time, and they're all at different latitudes, so it's not exactly the same time. So there's patches of time where a few of them will overlap. You can see that the instruments generally agree pretty well. That's good, right? It means modern RV spectrometers are capable of making these sub-meter measurements. What's not good is that the instruments all agree that the sun is changing in radial velocity. at the many meters per second level on a day-to-day basis. This is the problem we have to solve to detect 10 centimeters per second around nearby stars. Will the noise sources be the same? No, they will be different. Turns out pulsations and granulations are gone, right? We cannot detect the amplitude of pulsations and granulations around such tiny stars. So that's good. You can almost zero out some noise sources. But then some of the magnetic activity becomes much more prolific and much more complicated around the M dwarfs. They have to be simultaneous and they have to map to the radial velocities. And absolutely, but we don't quite know how to do that yet. The other thing we had to worry about, which I did not think we had to worry about, was a fire on the mountain, which I hope none of you ever have to worry about. There was a fire on the adjacent mountain, and we were told, hey, it's there, but it's not going to move that quickly. It moved very quickly. It just went through the underbrush, caught up. Kitt Peak would have gone up in flames, except there were firefighters who were parachuted in literally and who fought the blaze for a couple of days, staying there and standing there, right? So that's what it took to protect that mountain. Of course, this is completely disruptive for any working instrument, so you have to warm it up, cool it down, restabilize it. But I think these are the other challenges that instruments have to deal with and people who build instruments have to deal with, because we're often at remote locations, and as climate changes, as the world warms, these sort of incidences are going to become more common. But talking about sort of stellar activity and magnetic fields, all these phenomena largely are driven by magnetic fields. So, can we probe magnetic fields directly to infer the importance of these on the radial velocities? We have made some progress with HPF on this. So this is a Zeeman-sensitive potassium line that we've looked at with HPF, and you can see that we can track a small magnetic patch on those stars moving or sort of rotating in and out, right? So we're actually measuring the Zeeman splitting of this line, or rather the equivalent width changed because of the Zeeman splitting of this line, and we can sort of infer both the rotation period and the fact that there is a magnetic patch that goes in and out. This is something that is very hard to do photometrically, but we are able to do it spectroscopically. I also said early on that we should measure frequency, if we can measure frequency. So we built another spectrometer. This is a spectrometer. This is a spectrometer that our radio colleagues will identify with, right? This doesn't look like an optical or near-infrared spectrometer at all. This is a heterodyne receiver and a heterodyne spectrometer. But essentially, we take sunlight, put it through optical fibers. We actually beat it against a laser, which scans. But the innovation is that that laser also beats against a laser comb. So at any point of time, we know the frequency of that laser extremely well, and we can create our resolution of 1,000,000 spectrum of a chosen solar line. And this is one of those chosen solar lines with exquisite time tagging or exquisite frequency tagging along the axis. So this is an effort that we have with our collaborators to actually try to tease out the subtle magnetic variations of these of the sun, because we understand the sun pretty well. We have ground reality in the sun. If we treat the sun as a star, can we figure out how to correct for radial velocity noise from the sun? In the not so far future, well, 20 years, we're going to have the Habitable Worlds Observatory. We might have LIFE, which is an infrared mission. But before that, we will have the ELTs. We'll have at least some of the ELTs, right? And these are going to be great for terrestrial planets around M dwarfs. This is going to be fantastic for terrestrial planets around G and K dwarfs. And this mission will be able to do terrestrial planets in the solar neighborhood around any types of stars. But the important thing is we don't know where they are. And to find them, radial velocities is our only hope. The other thing I want to sort of mention in my last slide is that it's a real honor and privilege to give this talk, but it's really teams that build instruments. It's not single PIs. It's not single faculty members, right? Students, postdocs, talented engineers, observatory staff, colleagues who are fellow faculty members. It really takes a village to build these instruments. Thank you.
How do you take care of multiple planet pulls on the star?
Great question. So if the planets are not interacting, then it's just the signals just coad. So if you, in a periodogram, you'll just see separate peaks.
Okay.
So if you take out the dominant peak, then you can see the other peaks.
So something is closer, that's actually pulling it more.
Yeah.
Something is away.
Well,
pulling it
if it's more massive, yeah. But if the planets are in resonance, now it becomes a more complicated problem. Then you actually have to solve the full n-body dynamics, and then either infer, forward model it, or you take the data and then you sort of fit the model. So, but in most cases, the planets do not interact with each other that much. So we can essentially treat this as a linear addition problem.
So how much of modeling actually goes into pulling out the stuff?
A lot.
A lot?
So for the more massive planets, very little, right? You can do a Lomskargel periodogram. The period is the peak is right there. When you're looking at terrestrial mass planets, you might be working with data from 3 or 4 different instruments. You have to worry about stellar activity, so you're probably throwing Gaussian processes at it. But also multiple instruments, multiple wavelengths. So the Gaussian processes have to be chromatic. You have to worry about that the Gaussian process kernel is not so flexible that it just eats your planet signal. So a lot of modeling has to go into it for the tiny signals, less for the big signals.
Okay.
So this is about the tidal tails you talked about, right? I mean, so is that can be some sort of a propeller effect because of the rotation, and in this kind of Roshlab overflow, the matter is sort of churned out rather than
The helium detection?
Yeah, helium.
Yeah, so I mean, different planetary systems and different stars will have different signatures. So one of the tricky parts about the helium detection is it's not just about the planetary exosphere, it's also about the EUV radiation from the star, because you have to excite helium to this metastable level from which it can absorb, but you don't want to completely like excite it away. So there's some interplay of a sweet spot between there's enough the exosphere is big enough, or there's outflow, and the star is able to provide the right radiation.
Okay. And so that's the reason the tails are developing. And
Yeah, I think it's an interaction with the stellar wind and the co-rotation. In this case, I think that planet is low density enough that it's overflowing its Roshlab, so that enables that sculpting better.
Okay, thanks.
Are there any questions from our colleagues? You just unmute yourself and ask a question if you have. Yeah. While we're waiting, I have a question for you. It was very interesting and very exciting things. Can you give us some numbers out of, say, maybe 3,600 or so, where you said, how many do you think will fall into this range where you are looking for?
Yeah.
Percentage, right?
Right. So remember that most of the planets, the 5,000 planets, most of it came from Kepler and TESS, and Kepler was a deep field that looked, they could look many hundreds of parsecs away. Those planets that are hundreds of parsecs away are not the planets we're interested in, right? Because the telescopes that we're going to build simply do not have the diffraction limit to image them, right? So we're interested in the planets that are within 20, 30 parsecs, maybe 50 parsecs, if we are generous. And of those, Eta Earth, which is the number of terrestrial planets in habitable zones around sun-like stars, the rough estimate is about 20%, let's say. Huge error bars, but 20%. So there should be a number of systems that we will be able to detect planets in, many, many tens, in fact. But in reality, of course, selection bias and detection statistics, but we should be able to find dozens of planets for follow-up for future facilities.
Yes. Okay, I think that's it. All right. Thank you, everyone. Thank you again. There are no further questions.
Take a minute to get speaker. This is a 40 years of asset as a platform. And
Thank you.
request everybody to join for the team. Yeah.
Sorry, Suvrath, for missing your excellent colloquium.